So here's a weird little video. Try to ignore my hand. It's kind of tragic. Fingernails are a little sad. Let's talk about atomic structure, and then we'll follow it up with another short video about bonding. Those are the two main things we need to know before we can do the organic stuff later on. So first, let's deal with the particles of the atom. So all matter, as you know, and we've talked about this before, is composed of atoms. Now, there are some 88 different kinds of atoms, 88 elements worth, right? So the question is, if there's 88 different kinds of atoms that we call elements, what makes them all different? Well, the only difference that there can be is in the number of subatomic particles. So we're going to talk about subatomic particles. The subatomic particles are going to be what defines the atom and therefore what the element is. Each one of those elements has its own particular characteristics, which means who it bonds with, how often it bonds, how reactive it is when it does chemistry, that kind of thing. And it has everything to do with these subatomic particles. Okay? Now we've talked about what they are. They are, number one, probably most important, protons. It's hard to say one's more important than the other, but it is the proton that determines what type of atom it's going to be. So the number of protons determines the atom's type, which one of the elements it's going to have. So protons, as you know, have a mass of 1. And that 1 is a unit called atomic mass units, AMUs. So it weighs 1. All you really need to remember is when you're adding up the mass, just add up the protons, and then we're going to later on add on the neutrons too. So protons equal 1, and they also has one positive, we'll just put a little plus there, positive charge. It's got a full positive charge. All right, that's the other thing about protons. So protons, in every case, are going to count. You're going to use protons to count the mass of the atom, and you're going to use protons to figure out the charge of the atom, because the proton's the only thing that has both mass and charge. The other particles are going to have one, but not the other. All right. One of those other ones is neutrons. Neutrons also have a mass of 1 AMU, atomic mass unit. All right, so when you figure out the mass of the atom, you're going to add those two things together. So an atom's mass, atomic mass, equals P's and N's. All right, you're going to add the protons and neutrons together. If I have 10 protons and 10 neutrons, that atom has a mass of 20 atomic mass units. All right, it has an atomic mass of 1 neutron, and it has absolutely no charge whatsoever. That's why it's called a neutron. Protons and neutrons are made out of the exact same things, the quarks, but it just so happens that the quarks are spinning in different directions, and so one of them has a charge, one of them absolutely has no charge. Okay, so don't worry about neutrons when you're figuring out charge, but worry about neutrons only when you're figuring out mass. Okay, and we'll talk about a little bit more about that here in a second. All right, so the most important particle that has to do with what the atom is going to do for a living is electrons. Electrons are what's going to actually cause chemistry. Almost all chemistry is based on the electrons, what the electron's about to do and what it's going to do next, and if it's satisfied, and if it's the charge is neutral and all of those things. So we're going to worry a lot about the electrons. Most of chemistry that we do in biology has to do with the exchange of electrons, rebonding after you lose electrons, that kind of thing. So the electrons have no mass that we're going to worry about. The mass is so infinitesimally small that it is not even worth dealing with. All right? They have no mass worth worrying about, but they do have a full negative charge. One negative charge. All right? And that's important. The important thing to remember is that the negative charge of an electron is exactly the same in magnitude as the positive charge of a proton. And what that means is if I have a plus and a minus, that's going to equal 0 charge. You're not going to be able to feel it. Okay, so they're going to basically cancel each other out. If I have 11 protons and 10 electrons, right? Protons, electrons. This is going to equal what? Think. That's going to give you 1 positive left over. So whatever's left over, whatever charge there's more of, that's the charge of the overall leftover charge. Okay? This is going to be important for later on. When we talk about ions, let's just put that right here. An ion is an atom with a leftover charge. Okay? It can also be a whole molecule with a charge, but we'll worry about that later. An ion is an atom with a charge. All right, so far so good? So these are the particles. These are their sort of properties, their characteristics, and now we're going to talk about how they go together. Okay? So first of all, let's talk about the nucleus of the atom. The nucleus of the atom is at the very center of the atom, and it's the only place that it has charge. No, I'm sorry, it's the only place that it has mass. All right, all of the massive particles are in the middle. They're called the nucleons. So let's say we have a proton, a proton, a proton, and a proton, and a proton. Let's just put 6 of them. 1, 2, 3, 4, 5, 6. All right, that is the nucleus of a carbon atom. We're going to talk a lot about carbon. If there's 6 protons, that is going to be carbon. If there's 7, that's going to be nitrogen. If there's 8, that's going to be oxygen. So in other words, the number of protons in the nucleus is going to be what determines the element, whatever one of the 88 types of elements there are. It's going to be determined by the number of protons. All right, determines the element. So this one has 6 protons, and what that means is that equals carbon. Okay, and you'll find all that on what's called the periodic table. How many protons equals what named element. Okay, so also inside of that nucleus are a bunch of neutrons. Okay, so 1, 2, 3, this marker sucks, 4, 5, 6. Okay, so collectively we have 6 protons, 6 neutrons. This wad of massive particles is the nucleus. Okay, nucleus. Overall, this thing has a mass of what? 12 atomic mass units. 6 protons plus 6 neutrons. Right? Okay, so that's the nucleus. That mass doesn't have to always be, for instance, carbon doesn't have to have a mass of 12, but it does have to have 6 protons. What can change is the number of neutrons. If an atom has a different, we'll just put different like that, different than normal mass. And if I've already told you that a carbon atom has to have 6 protons, but it has a weird mass, let's say it's not 12, let's say it's 13, what that means is it must have an extra neutron. There must be one more neutron in there than normal. And that happens. These are called isotopes. If an atom has a different than normal mass, it is an isotope. All right? Do not get these two words mixed up. An isotope is not an ion. Remember, an ion is an atom that has a full charge. That means it's got one or more electrons missing or added. In this case, we're talking about different numbers of neutrons due to different, and I'm going to put different again like that, due to different numbers of neutrons. Neutrons can be different, right? So carbon 12 is normal, okay, because most carbon on Earth has 6 plus 6, 6 protons, 6 neutrons. But there are quite a few carbons out there that are carbon 13s and carbon 14s, okay? Carbon 13, of course, has 6 protons, but it's got actually 7 neutrons, which makes it 13, right? 6 and 7 is 13. There's also what's called carbon 14. It, of course, has 6 protons, because all carbon has 6 protons, but this one actually has 8 neutrons. Okay, so that's a super heavy carbon. Carbon 14 is a heavy isotope of carbon. It's used oftentimes in dating, you know, the age of a bone, when some bone was left behind by its owner or whatever. All right, so that's the nucleus. Now let's talk about electrons. All right, electrons. Electrons are by far the most important factor in determining what an atom is going to do for a living. But at the same time, an electron is also attracted to the protons in the middle. So really the protons attract the electrons, and then the electrons cause chemistry to happen. All right? So it is the protons that are going to attract them, because remember, positive charges and negative charges attract each other. And so when we have a nucleus, and let's go back to carbon. Well, let's do oxygen this time. Let's say this is an oxygen atom. Oxygen always has 8 protons, all right? And typically it has 8 neutrons. And let's just have that fill in for the nucleus. So this is an oxygen nucleus. Electrons exist in very specific energy shells, let's call them. Energy shells that are basically orbiting, meaning going around and around and around and around and around like that, super, super fast. Exist in specific energy shells orbiting the nucleus. Okay? So what I'm going to have you always do is make a nucleus neutral by putting the same number of protons and electrons, and then we're going to look at it and determine overall what that atom's going to do once you have it neutral. Okay, so here's what neutrality is. Neutral atoms have equal numbers of protons and electrons. Okay. Protons positive, electrons negative. So if I have 6, well, now I guess we're doing oxygen, 8 protons, and I match that with 8 electrons, the overall charge should be 0, right? So what we're going to do is figure out, where do I put these 8 electrons? Well, there's a rule. Like all things in science, there's some sort of rule. So the rules are this: electrons only exist at specific orbits in the shells. And let's look at it this way. Shell 1 holds 2, exactly 2, and it has to be full. In general, an atom is going to do everything it can to fill that first shell with 2 electrons. Once that shell is full, then you have to move on. The next electrons have to move on to the second shell, in that order. The second shell holds 8 electrons, and it has to be full. An atom's going to do everything it can to fill up that second shell with 8. Okay? Now, if need be, if it's a big atom, that has, you know, more than 10 electrons, you have to move on to shell number 3. Okay, shell number 3 is always going to hold, if it starts to be filled, 8 electrons. Okay, so all you have to remember is 2, 8, 8. Those are the first 3 shells. Those shells are going to be, an atom's going to do everything it can to fill those shells. Okay, so let's just start with oxygen. Let's say there's a shell here, goes around, 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 around. There's an imaginary shell out here, goes around, 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 right? Each one of these shells is at a specific distance away from that nucleus. The nucleus is the positive pole. Right now it's got a positive 8 charge because it's oxygen. If I want to make this thing neutral, I have to put 8 electrons in there. The first 2 can go here. 1, 2, right? 2 electrons. And now I have to put 6 more, right? I got to get 6 more. So I'm going to pair up the next ones. 1, 2, 3, 4, 5, 6, and then I'm going to leave these 2 by themselves, and I'll show you why in a second. So that's 1, 2, 3, 4, 5, 6, 7, 8. So now I've got a neutral oxygen atom. This is what's called a normal. Normal because it's got a normal mass, and it's neutral because it's got the same number of protons and electrons. This is a normal neutral oxygen atom. Okay? One oxygen atom, as long as it's neutral, is going to be built exactly like that. That's the configuration. Let's do another one just real quick, and then we'll move on to some other rules. Nitrogen has 7 protons, always. And normally, it has 7 neutrons. Okay, so this is a normal nitrogen. It weighs 14. It weighs 14 atomic mass units, this one. Okay? Now, I'm going to put the shells around there. 1, 2, I think I'm only going to need 2 to make nitrogen, so we can ignore the 3rd shell this time. Now, what I want to do is make this thing neutral. So if I have 7 P's, I'm going to have 7 E's to have no charge, and that's what we're always going to do, make it neutral to start. So 2 of those electrons have to go there. Now it's full, right? If I'm going to get 7 altogether, I have to put 5 here. All of a sudden, I've got a neutral atom. I've got 7 negatives. I've got 7 positives. That is a normal, neutral nitrogen. It's got a nitrogen to it. Normal, neutral nitrogen is built exactly like that. But remember, you go all the way around. Okay? Well, the problem here is that nitrogen is never going to spend any time in this condition. And the reason for that is because 5 is not full. This shell right here is not full. Let's go back up here to oxygen. 6 is not full, right? So 5 is not even close to full. So what we have to do is figure out, well, how am I going to fill up that shell with 8? And that is the rest of the story. The rest of the story has to do with bonding, and bonding is going to take care of these problems when atoms don't have a full outer shell. Before we go on to that, let's practice this a couple more times. I'm going to say, I will ask you on a quiz, I'll say, okay, build a hydrogen atom. Hydrogen is the simplest atom. It has 1 proton. It has 0 neutrons. Hydrogen's kind of a weirdo. Hydrogen doesn't need any neutrons normally because 1 proton doesn't need holding together. It's just 1, right? Neutrons help hold the protons together inside the nucleus. So if I'm going to make this a normal neutral, I'm going to basically put 1 electron out here, right? 1 positive, 1 negative, that's 0 charge. That's normal neutral hydrogen. Helium, on the other hand, is number 2. Helium typically weighs 4. Okay? So if it weighs 4, that means it's got 2 protons, or neutrons, I'm sorry. So helium normally weighs 4 because it's got 2 neutrons, 2 protons. Helium needs 2 electrons to be neutral, however, because it's got 2 positives in here. So I'm going to put 2 electrons there. It's got a full outer shell. Helium loves its atomic number because not only does it have a full outer shell when it has neutral, but when it's neutral, it doesn't have a charge either. All right, and we'll talk about that in the next little video. Let's do one more. Oh gosh, let's do sodium. Sodium is number 11. Sodium typically weighs 22, I think, so it usually has 11 neutrons, okay? In general, when I draw an atom, you're going to say, well, where are the electrons? Well, you have to decide how to make this thing neutral. Right now, it has a normal mass of 22 atomic mass units, but it's not neutral yet because I have 11 positives. So in order to make this thing neutral, I've got to add 11 negatives, or protons. So I'm going to put 2 protons in the first shell. I'm going to put 8 protons in the second shell. That's 10. And then I have to add 1 lonely electron in shell 3 because this is full with 2, right? First shell 2, second shell 8, third shell 8. I've got 1 lonely electron here because these 2 first shells are full, and now I've got 11 pluses, I've got 11 minuses. This thing's neutral. Well, sodium has a particular problem because it has a shell that needs 8, and it's only got 1 in it when it's neutral. And we're going to talk about that in the next video.